Welcome everyone. Opening the video, we see the author connecting a clear water pipe into the device pump. Next, he clamps the positive and negative terminals to the metal faucet system to create a ground connection. A digital multimeter is being used to measure the AC voltage generated from the system. The parameters on the LCD screen are constantly jumping, showing that voltage is being generated. Surprisingly, this appears to be a type of generator or a homemade heater, utilizing the magnetic field motor of the pump. The basic principle here might be reversing the process of converting electrical energy into mechanical energy in a magnetic motor. Quick cutscene. The author proceeds to disconnect the power of the green water pump. Placed on the well's edge, he pulls the plug from the power strip, turns off the safety switch before starting the device disassembly process. Ensuring electrical safety is the first step, and the most important one, in any process involving deep hardware modification. The device is brought to the workbench. He uses a specialized Makita impact driver with a screwdriver bit, 3 screws fixing the cooling fan cover at the back of the motor are removed very quickly. Next is the technique for removing the casing. He uses 2 flat chisels, sharp ones, and a wooden mallet to lightly tap and separate the joints. Levering symmetrically on both sides helps the cast aluminum cover stay straight, protecting the internal rotor shaft from bending or breaking. The casing is lifted off, revealing the stator core with copper coils, wound very tightly and coated with insulating varnish. The author lifts the rotor assembly out of the stator chamber. We can see the steel shaft and heat-dissipating bearings are still in good shape. The cordless drill is used again to remove the cap of the brass pump chamber, where it makes direct contact with the inlet water source. Inside the pump chamber is the centrifugal impeller. Due to long-term exposure to water, this part is heavily rusted. An extremely clever solution, using a mini gas torch to directly heat the impeller hub to expand the metal. High temperature breaks the rust bond. Then, needle nose pliers are brought in to remove the shaft locking snap ring. Right after the snap ring is the mechanical seal assembly. He gently uses the flat screwdriver to pry the rubber gasket and ceramic ring. Removing the pump seal requires dexterity to avoid scratching the shaft. Next, the hex bolts fixing the aluminum flange are being removed. He uses an automatic ratchet wrench with a hex socket, performing a very decisive arching motion to loosen all the bolts. After loosening the bolts, prying the final flange cover off the stator is repeated, using the familiar flat chisel tool. Now the entire outer casing has been stripped away. The focus now is only the stator magnetic core and copper coils. This is the heart of the electromagnetic induction system. From here, the modification process to transform the function officially begins. The author takes out a section of smooth copper tubing, 6 millimeters in size. This is the type of tubing commonly used in air conditioning refrigeration systems. He uses a plastic pipe, rigid PVC, as a round mold core, skillfully using hand force to bend the copper tube around it. Hand bending technique requires even strokes, so the copper tube doesn't kink, ensuring the cross-section for internal fluid flow. He winds exactly 3.5 turns. The number of turns of this copper coil acts as a heat exchange coil, or a fluid conduit. Specifically, the coils are being manually adjusted. The distance between the turns is compressed to optimize space. The magnetic chamber, the outer diameter of this copper coil is calculated to fit snugly into the empty space inside the stator magnetic core. Stator. The copper coil has been bent perfectly. The author slowly places it similarly into the gap of the stator magnetic core. The coil fits neatly inside. A deep modification detail. never seen in ordinary motors. Next is an unexpected material, absorbent medical cotton. He tears small pieces of pure white cotton. The cotton is packed tightly into every corner between the copper coil and the stator core, completely filling this layer of gaps. Meticulousness is shown as he uses his hands to compress the cotton, forming a filter or a liquid-absorbing core. A bottle of Castrol active motorcycle oil, 20W50, appears. Using a medical syringe, he draws up the oil solution. Each syringe of oil is pumped directly into the chamber. The cotton layer now acts like a sponge to hold the oil. The stator core gradually becomes saturated with oil. The main purpose is to create an environment for absolute heat dissipation and insulation for the system. 20W50 oil has high viscosity and good heat resistance. It is ideal for immersing a copper coil that generates high-intensity heat. The author places the aluminum flange cover back into its original position. The joints are carefully aligned to prevent leakage. A rubber mallet is used to tap evenly all around. The tapping force is just enough to compress the mechanical seals. The hex bolts are refitted. He uses an automatic wrench with a socket adapter to tighten with great force. The motor assembly is now completely sealed. The protruding copper tube is the only contact point with external fluids. Switching to the electrical circuit part, using a screwdriver to open the box cover, that houses the pump's starting capacitor. Inside is the connection system. He loosens the plastic wire nuts to release the terminals of the old capacitor. Each pair of green, black, and red copper wires is stripped and separated. The input circuit is being completely reconfigured. The original capacitor is removed. The author signals with his finger that this component is no longer suitable for the project. Instead, there are two square capacitors, specialized CBB61 units. He uses a glue gun to stick the two capacitor bodies together. Wires of the same polarity are twisted tightly together. This parallel connection technique helps double the capacitance. Increasing the capacitance value will create a large starting current, changing the magnetic flux range of the internal stator coil. The glue gun is used again to apply glue to the casing. The new dual capacitor assembly is fixed to the motor housing. This component change is the key to establishing oscillation, resonance for the electromagnetic field conversion system. He continues stripping the insulation from the wire ends, preparing to connect the new capacitor unit to the inductor system. The copper wire ends are stripped and twisted tightly together, connecting the dual capacitor assembly and the inductor. Plastic wire nuts are used. They help seal the connections, ensuring no electrical leakage. Connecting capacitors in parallel enhances the charging and discharging capability, creating an extremely powerful voltage pulse. 5. A large current will stimulate the copper core system inside the oil-filled housing to generate high-intensity magnetic fields. All connections are complete. Carefulness with insulation at this stage is a vital safety factor. 4. The author tucks the wire bundles into the technical box and puts the black plastic cover back in place. 5. The screwdriver is used once more to tighten the screws, completing the protection for the external circuit system. A wooden base is prepared. The modified motor assembly is placed neatly onto the base. The Makita cordless drill continues working, tightening the screws to firmly fix the motor base to the wood. Cut to an old amplifier circuit board appearing. This is a source of excellent recycled components for project systems. A high-temperature soldering iron and a solder sucker are being used rhythmically to desolder components. The author harvests a set of power transistors. These might be transistors or MOSFETs that can handle huge currents. A thick, finned aluminum heatsink is brought out. On the wooden block, the mechanical machining stage continues. The steel drill bit pierces through the aluminum layer, creating precise screw holes. Along the edge of the heatsink, aluminum shavings fly out continuously. These drilled holes are calculated, with equal spacing to install the power transistors. 5. Blowing away the aluminum dust. The contact surface must be flat and clean. To optimize the heat transfer capability, each transistor is placed over a hole. A screwdriver tightens the screws to press the components against the aluminum, for the power transistors are firmly fixed on one side. Good heat dissipation is the core factor for high current circuits. For when components operate at full power, they generate an amount of heat, massive, and this aluminum block will absorb and handle it. 5. The opposite side continues to be fitted with 4 more transistors, totaling a system of 8 parallel power transistors. The power of the inverter circuit is clearly taking shape. From this high-quality power control component assembly, a small copper wire is pulled out. He cuts and straightens it, a section to make a booster bar for the common current. Tweezers place the copper wire across the component pins. The soldering iron melts the solder to bond them into a single unit. This copper bar connects in parallel the pins of the transistor assembly, ensuring even distribution of the massive current load. The soldering iron glides very decisively across each component pin, being connected in parallel via the copper bus bar. This high-power transistor system will act as a powerful multi-vibrator electronic oscillator circuit. He flips the heatsink and bends all the remaining terminal pins of the power transistors on the opposite side. 1. Another copper current-carrying path is added to synchronously link the entire semiconductor system. 2-point soldering technique requires the solder joints to be thoroughly melted to avoid voltage drops when high currents are loaded. 3. Meticulousness is shown through each shiny solder joint. The power control board is gradually nearing completion. A third bus bar is soldered and fixed firmly to the top terminal pins of the electronic component strip. This parallel circuit architecture aims to minimize internal resistance and maximize the performance of switching current flow. Molten solder continuously fills the contact points. The oscillator circuit is ready to pump high-voltage pulses back to the wooden base. A hot glue gun is used to spread a thick layer of adhesive material next to the motor. 4. The heatsink and power transistor array are pressed firmly onto the wooden surface, forming an integrated control system. Now is the connection step. The power wires from the motor are soldered directly to the copper busbar system. This link will transmit the oscillation frequency from the semiconductor circuit straight into the oil-immersed magnetic coil. 6 power supply clips with red and black alligator heads are brought in to prepare for supplying DC input energy. The red positive power wire is soldered very carefully to the central bus bar of the power component array. The system is completely assembled. It looks like a small-scale static magnetic field induction heating station. The author moves the whole machine to the testing area, outside in the field where a water supply system is available. The device is placed on the edge of the tank. He begins threading the clear plastic tube into the lead of the copper coil. This clear plastic tube is connected directly to a household faucet for continuous flow. 2 alligator clips are clamped directly to the power source, starting the high-power inverter circuit system. The digital multimeter is turned on in voltage measurement mode, AC, to measure the output reading. 4. When the probes touch the output, the reading immediately jumps, displaying over 20 volts. The induction system is operational. As soon as the tap is opened, the cooling water flow through the copper core, makes the readings on the meter fluctuate interestingly.